Now here I'm going to choose my x and y columns for this model. Here you can see the x columns are things like the day of the week, the day of the month, the distance of the flight, the origin, the destination, stuff like that. And then this is somebody else. This is a shared cluster, so somebody snuck on my demo cluster here. I'm going to just wait until it settles down, and then I'm going to actually run a GLM. And so here you see in R, I'm calling H2O.glm and passing it the x and the y that we just told. The family is binomial, which means I'm going to get a logistic regression model, or a yes-no classification model is equivalent. N folds is 1, so it's going to skip cross-validation. And I've got an alpha of 0.25 and a lambda of 0.001. Those are the regularization parameters, which I can talk about later. And let's run GLM.
Is there a reason why, or perhaps this is just, how do I phrase this? Does it allow for traditional formula input?
It's done.
That's awesome. Does it allow for traditional formula input, H2O.glm, or do you have to specify explicitly the x?
Yeah, we didn't do that. We made it
y?
explicitly specifying x and y.
Okay.
Um,
Are there any plans to allow for just traditional R formula input, y tilde, or yeah, y
Right.
tilde?
It's an interesting question. So far we haven't done it. One reason, I can't even say that it was a constant, a deliberate reason to leave it out. But one reason that I can say that might make sense to leave it out is if you're creating terms that you're going to put in the formula, if you want to reuse them, it's more efficient to build it once and to remember it than to build it and throw it away and build it and throw it away. So a lot of people will actually, because H2O is a machine learning package that has lots of models, a lot of people will actually build a data set and then they'll want to use that data again on many different models like random forest, GLM, deep learning, and so they'll tend to not throw away the data. That's not really a real answer to your question. Honestly, I don't actually have a good answer to your question.
Yeah, I mean, that's okay. I mean, I'm sure people using it from other languages are not used to that type of formula input, so it may make more sense for them to just specify a vector of inputs and then the output. Thanks.
The only thing I would say in defense of Raphael here is that one of the advantages of using that formula notation is that it allows you to update models. There's an update formula. You use an update function to take a formula object and modify it and then task that into the routine.
Okay.
Okay. That's the only reason. That's the major reason why it's there.
Okay.
That came in with the blue book. Or it's not the white book. In S3.
Okay.
That's the only real reason. But that's pretty. Again, like you said, it's pretty idiosyncratic. At the time.
Yeah. So we haven't done it. I mean, what I'll say is that we are very driven by what people ask us for to do, right? So, the set of features that you see here, it's not random, right? It's not an accident. It's what we got pushed to do by customers, right? And so when we hear the same thing many, many times, and people have, a huge, drive to get something, then we'll prioritize it and work on it. And on that one, honestly, we just haven't had a whole lot of clamoring to get it. Probably because it's easy to just manually work around it.
Sure.
Well, you can always do things like subset. If you want to reduce your model, you just subset your X vector.
Yeah.
Or if you want to expand your model, you just add something to the X vector. So
right. And so that's
just a manual thing.
Exactly. So one of the things what we're looking at as a roadmap thing is better ways to build interaction terms. And maybe at that point it would make sense to revisit the question of formula.
When you're dealing with things like splines and other basis function in terms of columns and model. you're doing GAMs, for example, rather than GMMs. That's sort of where it goes.
Yeah, honestly, I'm not.
Well, what you're doing is instead of having like columns, so you have variables as columns, right?
Sure.
Each of those represents a basis function for the matrix.
Okay.
Okay? So now you're instead of having columns, what you're doing is replacing with functions.
I see.
Okay?
Yeah.
So that's basically. It's the same principle, it's just different. It's
Yeah.
fun to get through that.
Yeah. So we actually do support things like apply, or even just writing an expression to create a new column. So I think you could get the same effect if you did it manually in many cases.
In some ways, I'd say it may actually be better. Because it forces you to think about it.
Perhaps.
Nobody wants to do that.
And you want instant answers, you know?
Yeah, I mean, one of the things about working with big data that's interesting is if the data is big enough, you have to have some awareness of how many resources you're using, or you'll run out. And so if you make it too easy to just use up infinite resources with very few keystrokes, you might just do that. Now, in the case of generating new columns, I'm not sure that's the best example, because you might have 100 columns and generate 10 new ones. But people are also doing the other, which is they'll have 100 columns and they'll use those 100 columns to generate 10,000 columns, right? So you can really explode your data, and you've got to just be aware. And if you want to reuse it, then it's better to actually name the columns and not generate them synthetically, on the fly, and then dispose of them when you're done. So let's keep going. So I built a model, and now I'm going to use the 20% that I left out to make to use for predictions.
Oh, God,
That was so fast that I was questioning whether I actually did it, but I think I did. So let me, yeah, it did. There we go. So 23 million predictions, and here are like the first several of them.
It took longer to print than it did.
And here I'm going to calculate some standard quality metrics for a model using H2O.performance call. And here's a printout of the performance object. You can see that it's got things like AUC and F1 and things like that, and then the confusion matrix. And here we can get, I don't know if that'll, so my screen resolution's not right anymore, but if I shrunk it down, it would give us a plot over here. But ours not happy because the screen didn't fit. So this is one really, really simple example of how to
I want to
use.
slide it.
Sure, sorry.
Try again.
You think it'll work if I do this? Oh,
Hey.
And you can zoom in, or
Still
click
looks
zoom, and it'll open an
pretty
external
messed up.
window.
Yeah, at least you got something.
there we go. So just an example of how to quickly use H2O on big data from R, and how to get scaling using a cluster, but I'm driving it from the H2O package. And I could have, if I'd chosen a smaller data set, I could have done the same exact thing, just on my laptop. So this is the first demo I wanted to do. I've got a couple of other demos that I can show from R. Before I do that, though, I want to just give you a peek at the web UI as well. So one of the interesting things about H2O is, in addition to being usable from R, we can also use it from a web browser. And actually, this is a very popular way for people to use H2O that don't come from an R background. So here, using the web browser, we can get a nice view of the data set, a row-column view of the data set. And I can go click on summary, for example. And if I submit this, you'll see the cluster's doing some work, building summary statistics for my columns. And now it's done. And let's go click on origin, for example. And here you can see, here's a histogram of all the different airports that were origin airports and their frequency in the data set. When I was showing you GLM, I showed you from the R interface, but of course we could have run GLM from the web UI. In addition to running it, we can also look at the results. So let's go take a look at some of the model results. Let's go look at the model here. And here you can see, here are the coefficients of the GLM. These are also, of course, available in R, but here I'm just able to browse them from the web UI, which is kind of nice. And here you can see the confusion matrix and the ROC curve as well from the web UI. So what a lot of people like to do is they like to automate things with R, but they like to use the web browser to cross-check what's going on and to explore and to just sort of help to visualize things. So, what you do is up to you. There's no right or wrong way. We try to provide lots of different ways of accessing the information and use whatever you think is the best for you. Okay, so that's my first introduction demo. What I'm going to do next is talk a little about GLM itself. So, and how we actually distribute it. So, you go back to PowerPoint, and the way that we represent data in memory is as vectors. And so, imagine this is just a really tall vector. In this airline's case I showed you, it's a 120 million row vector. And what we do is, as I mentioned before, we store it as a compressed columnar format. And what that does is it supports very, very fast on-the-fly decompression. And it also, because we're writing this stuff in Java and we're distributing around the cloud, it's helpful to, for those of you that are programmers, to use Java memory model semantics. And I showed you a cluster of 4 machines, and actually, you can imagine these alternating colors as representing different nodes in the cloud. And what we're doing is we're splitting that vector, that 120 million rows, across the machines in the cloud. And each of those colors represents one machine. And here, taking it to the next level, now one row represented by several columns is stored on one host. So one machine in that cluster stores one entire row. Or I should say that entire row lives within one machine, is what I meant to say. And really what we're doing is we're striping the data around the cluster. We're striping it in a very, very simple way. We group the data into what we call chunks. A chunk might be 1,000 or 10,000 rows. It doesn't really matter. And they get basically, chunks get striped around the cluster. Every row lives in exactly one spot. What that means is that there's no redundancy. If one of the nodes dies, the cluster dies. But as you can see, because we've focused on speed and scalability and making things fast and using R to help automate stuff, going back to what customers have kind of pushed us to do, they've pushed us to make it faster and to deal with more data and to build better algorithms, and not pushed us as much to do HA, as an example. So that's the model. The model is one row stored in one spot. to maximize memory utilization. So that's kind of the memory side. Now if we talk about the CPU side, I mentioned before that we implement a distributed MapReduce, and that's actually built on top of distributed fork join. This distributed fork join, this is like a lot of computer stuff. I don't know if I want to get into it too much, but basically in Java 7, there's this concept of fork join, and what it's trying to do is to map pieces of work to threads that are available. And so you can think of these tasks as a piece of work to be done, and basically this task at the bottom node here gets mapped to a chunk of data, right? So it's mapping chunks of data to tasks or to threads that are available to do the work. And that's how we get parallelism. And it's done in a MapReduce kind of a way, and it's distributed across the cluster. Yeah, question? Oh, no question. And so we do this MapReduce stuff across the cluster, but then we also do it internally as well. And here you can see the tasks at the bottom, these leaf tasks, get mapped to chunks, and this is where you see something actually happen, right? Above here, it's basically management work, and at the bottom, it's producing, it's doing math, it's running the algo. And the point of showing you this is really just to give you a sense of some of the infrastructure that's involved in order to build the algorithms and to have them distribute efficiently, but also to say that we've done that work, and so adding new algorithms, you can take advantage of it, right? So if you wanted to write a new algorithm, the work to do this, the software engineering to come up with a framework like this, to come up with a distributed MapReduce, in-memory MapReduce, to come up with the mapping of chunks to tasks, we've done that. So it's possible to add new algorithms without having to redo all that again, which is nice. We take advantage of it.
This is probably a stupid question.
Yeah.
Are you hitting, like, do you have one primary machine that's then sending everything else off? I just deal with one machine?
Yeah, no, that's not a dumb question at all. It's a great question. The question was, is there a primary that's sort of the master, the cluster master? And the answer is no, not really. Now, so H2O is a peer-to-peer architecture. All of the nodes are effectively peers. You can start work on any of them, and doing that, we'll utilize the rest of them to run. However, the mode that we really test the most is having all of the work being routed through one of them. So even though there's no actual master from a software perspective, there's kind of a, by convention, we test with having a master. Even though it's not really a master. So that's how I would recommend that you guys run as well. Yeah? No, not again. Okay, sorry. So that's kind of some of the computer stuff behind GLM. Let me talk about some of the math a little bit as well. And I'm going to confess to say that I'm a computer guy, not a math guy. But I'll try to describe how we actually have distributed our GLM to make it fast and to make it scalable. So GLM, the GLM fitting or model building is basically, it's trying to come up with a set of coefficients that represent a linear relationship between your predictor variables and the model. And so what we're trying to do is basically take this classic log likelihood GLM and adopt some of the new fancier features like regularization, L1 and L2 regularization, lasso and ridge regression regularization that have been worked on by guys like Rob Tibshirani and Trevor Hasty, and we're very fortunate to have them helping us out. So taking these two things and basically coming up with this expected value, model where you've got beta coefficients representing the influence of the different predictor values. And so one of the interesting things about GLM versus, say, random forest or deep learning is, GLM, it's very interpretable. So, if you think about different attributes of a model, one is how good of a prediction am I going to get? But another, especially in industries that are regulated, I don't know if there are any of those in this state, model interpretability is important, right? If you're gonna clean somebody's clock, they might go to the gaming commission and ask, what, was it rigged? And if you give them a deep learning model, it's damn hard to tell, yes or no, was it rigged? But with a linear model produced by GLM, you can say, here are my coefficients. This is exactly why you got the answer that you got. And no, it was not rigged. It was totally above board. So, just from a high-level point of view, this is what GLM in H2O is doing. And let me just go to the next slide here. Let me talk about some of the features of the GLM that we have. Different families. Gaussian is typically used for numeric regression. The binomial family is typically used for logistic regression, or otherwise known as binomial classification. Less so in ridge regression, I kind of mentioned. We can also use them together in what's known as elastic net in the statistics crowd. We have a fairly new capability from some of the research, I believe, from Shirani called strong rules for L1 regularization. And what that does is it lets you make a guess whether you can eliminate particular predictor variables early on to get even more speed. So L1 regularization is about eliminating variables from your model. It's about trying to come up with a resulting model that has fewer numbers of variables in it than the number of predictors that you started with, because it's, if things are not contributing too much and you can lop them off, it makes your model even more easy to understand, and that can be good sometimes. It can also let you solve things that you otherwise couldn't have solved, right? If you start with many thousands or tens of thousands of columns and you can chop a bunch of them down, you might be able to get a solution where without using L1, you'd end up with a thing that just runs forever, or uses too much memory or whatever. Efficient handling of categorical variables. So that's kind of a neat capability of H2O that I would encourage you guys to explore. This is one of the things that was actually suggested to us by a customer. And I guess coming from R, you probably are already used to this, but basically, you can imagine if you've got a categorical variable, some machine learning frameworks don't let you treat it as a category. They make you expand it, do a one-hot expansion into a bunch of columns, one for each level. So for example, scikit makes you do that, actually. Scikit learning from Python. Which is a little, it can be painful. It's nicer not to have to do that. So one of our early customers said, you've got to implement this. And so we did. Efficient n-fold cross-validation is also something that we support, especially for GLM, because it's kind of easy to work it into the implementation. The elastic net parameter, the alpha and lambda, the alpha and lambda that people are used to, we support. We've got a lambda search now that if you want to just tell GLM, if you want to tell the overall GLM solver, go do more work and try to find the best lambda for me, it will do that. Okay, so here I've got just we looked at some of this already, but I won't spend too much time here. But basically, just examples of what calling GLM looks like from R. This guy I didn't mention before. This is probably worth pointing out. So we've got a couple of little features here, as.h2o and as.data.frame, that are neat and let you take small data files and move them from R to H2O or vice versa. So if you've got here a regular R data frame, here I'm just creating iris as a data frame. Here, using this as.h2o is turning my regular R data frame into an H2O data frame. So it's just a convenient way of moving the data, from the front to the back or vice versa. As.h2o and as.data.frame. Here you can see the number of iterations. This is the number of sort of large outer iterations. You can specify it to be a maximum value. Here are the ways of specifying the regularization. Cross-validation, just n folds equals 5. And here are some of the outputs. I would say the coefficients are probably the most important output. We've got coefficients as well as normalized coefficients. So if you want to be able to compare the magnitudes of the normalized coefficients, we can give you that. And then in terms of the quality of the model, things like null deviance, residual deviance, AIC, things like that. And then, of course, AUC and confusion matrix, which I showed you during the earlier demo. And here's a picture, actually, of the way that H2O's GLM, the way that the life cycle works. And this part I kind of highlighted because this is where the majority of the time goes. This green part is what we parallelize, and the red part is actually not parallel. It's done on a single node for one iteration, or for one model, one GLM model calculation. So, at the start, it's basically trying to calculate, the null model. And then if you're doing a lambda, if you enabled lambda search, this outer loop here is doing a lambda search and trying to get the next lambda. And then it wants to calculate the active predictors, which might, using strong rules, throw some away if you've enabled strong rules for L1. And then the distributed calculation is calculating a gram matrix. And that's done for each of the leaf nodes. And when that's done, this is the part, this green part, where all of the nodes light up, right? When you saw the perf bar, the perf bar was the CPU meters. When that lights up, this is really what it's doing. And when that's done, it goes and does a Cholesky decomposition and an ADMM solution for the L1 regularization using ADMM. And then it calculates some gradients and does KKT checks to make sure that it was you got a valid solution. And once you've kind of gone through this enough times, you've got a model. So this is it's kind of an interesting picture just to see how do you actually which pieces are distributed and why and how. And so really this one here is the guy that does the majority of the work. So if we go to the next slide, I can show you some of the runtime costs. And here you can see CPU and memory costs for GLM for the green part, this distributed calculation of the gram matrix, and for the red part, which is the single node Cholesky decomposition. Now, one of the reasons that we can do cross-fold validation kind of efficiently is we can do these in parallel, this red part. So if you start a bunch of cross-fold models, once they've done the distributed part, this red part can be done for multiple models kind of in parallel, which is a nice little cheating factor from a speed point of view, a little optimization. So lots of numbers here, but really the thing to point out is the memory is sort of order n squared, and the CPU time for the Cholesky is order n cubed. And so those are some of the driving factors behind the cost of running GLM and H2O for this implementation.
Which is why fewer predictors are better in this case.
Sorry?
Which is why fewer predictors are better in this
Yeah,
case.
yeah, which is why fewer predictors are better. Now, we do have some interesting cheats, though. Like, for example, we have a largest categorical column cheat in there. So we can take if you've got a categorical column, we'll pick the one that has the most categories and actually pull it out and sort of do that one for free, because it doesn't, it doesn't need to be actually part of the matrix. We've got a way out of that. But little tricks like that aside, this is the cost of doing it. And some best practices, GLM is of course the bread and butter of data science. So it's good to know kind of what things to look for to know if you got a model out or not. But I would say what you just mentioned, tall and skinny data sets are what this is really strongly optimized for. I'd say lambda search is something you should give it a try. It's definitely going to help you if you want strong rules. And max predictors, you can turn those both on if it's taking too long. One interesting thing about lambda search is the way that it works is it starts at lambda max and then iterates down from there. And lambda max is basically the highest, it's the smallest value of lambda where all the predictors get knocked out. So basically, evaluating that model is very cheap. So what we'll do is we'll start there and then reduce the lambda, reduce the lambda, reduce the lambda. And as you do that, more predictors are enabled, and so it takes longer to find a solution. So 90% of the runtime when you're doing lambda search is with the lower lambdas, and you can specify max predictors and strong rules to help with that. Then a couple of other points that are interesting. You definitely want symmetric nodes in your H2O cluster. H2O, it's the way it distributes resources, it's assuming that they're all going to be the same. So you definitely want that. Bigger nodes, because this ADMM and Cholesky part that I was showing here, because this is single threaded, and the memory requirements as here are order of number of predictors squared. If you've got a lot of predictors, you want an individual node to be big enough so that this single machine part of the workload has enough resources to run comfortably. And then the last thing to kind of keep in mind for the current implementation of GLM is that we throw away rows that have NA values. So you should impute your data before you run. We might change that. I'm not exactly sure if we will or not. We probably will. If we make a change there, it would be on our next generation of software and probably not on the one that's currently in CRAN. And then some things to watch out for. If your AUC is too good or too bad, that's a sign. If your deviance explained, which is the thing that's the model is trying to, deviance is what the model is solving for. If it's too close to 0 or 1, if your objective function is too far to the edge, that's bad. NAs in your data, I mentioned. Another thing to pay attention to is if GLM stops early for a particular lambda, then, well, if it's stopping early, that's usually a good sign, actually, because it means it found a solution that it liked. If it runs to the maximum number of iterations, then usually it's worth investigating whether you've got an answer that's good. And finally, just a benchmark slide. I don't really want to spend too much time on this other than to say it runs pretty fast. I showed you an example of running a large data set, and it scales very well. So GLM, you can see that the yellow bars and the black bars are comparable with each other. The bar with the smaller runtime has 3 times the amount of resources of the bar with the larger runtime, so yellow and yellow and black and black. And you can see that the runtime is scaled very well. These were done on EC2, those numbers.
And we're saying that it scales linearly, basically?
It's pretty close to linear. I wouldn't say it's perfectly linear, but it's pretty darn close. It's good. It's certainly, GLM scales very, very well because as long as the green part of the work is the majority of the work that I showed you in this slide over here, it's going to scale really, really well, right? If this is where it can slow down. But again, if you've got more machines and you're doing more cross-val models and so, et cetera, you can get those parallelized as well. So it's just a different level of parallelization. Okay, so from a slides point of view, that's all I had to show you guys. I'd be happy to show more examples or take any questions. So let me get some feedback from you guys on what you'd like to see, or we could talk about different models too, not necessarily genome. Yeah, question.
So because I'm not familiar with the fork join framework,
Yeah.
I know with MapReduce you can optimize your MapReduce by allocating the way you break up your data. How you're saying that it does it on its own?
It does it on its own. So what we do is when we parse data in, we break it up into chunks. And those chunks are the parallelism level. So if you've got a really small data set, you've got to be kind of careful about this, actually. Let me give you an example. So if I were to take, here you can see my cluster, actually. If I were to take the iris data set, which is a pretty famous data set from, I think, the 1920s or 30s, that data set has 150 rows in it. And if I were to use that data set on H2O, what would happen is all of the data would live in one chunk. And what that would mean is, even though I've got all of these clusters of resources, you'd probably only see one green bar, like just one little bar, because the MapReduce fork join would ultimately only find one chunk of data to work on. And so what that means is that you're not going to be able to take advantage of much parallelism. Now, fortunately, it's such a small data set that you can run any algorithm quite fast anyway. But when we parse in data, what happens is the parse algorithm actually is assigning rows of data to chunks and then assigning chunks to nodes. And the number of chunks is really, and their distribution is really what determines ultimately the parallelism. But for any big data, it's usually fine, right? It's only when you've got a tiny bit of data that you've got to be worried, or if you have an enormous cluster that you've got to think about these things. But we try to make it invisible for you. Any other general questions, or yeah?
Yeah, so you obviously use a static piece of data, that's CSV in your example.
I did.
And you were talking about the possibility going forward of hooking into databases and things like that.
Correct.
Wouldn't it, like, I'm maybe really ignorant on this, but wouldn't it be just as feasible to bring in the RODBC package, for example, create a connection in your R session, and then just paste the query in that syntax into the H2O import statement?
That's an interesting question, and let me bring this picture back. And what you want to think about, let me just repeat the question. The question is, could you use from inside of R an RODBC query to read the data and sort of hand it off to the H2O import reader thing? And the answer to that is you really don't want to do that, because for really big data, you don't want the data flowing through R. You want the data to be ingested by the cloud directly from the data source. If you put R in the middle, that kind of,
It's a bottleneck.
it creates a massive, massive bottleneck, actually. You can imagine, you could have a 64 node H2O cluster. You really don't want one little R guy in the middle. That's going to be super slow. Now, technically, could you do it? Yeah, you could technically do it. Do you want to? Probably not. But we do actually exactly that for a lot of our examples. So you can do importing a file. You can also do uploading a file, which is exactly what you just suggested. And we do that plenty for examples, right? It's super convenient to pull a file from your laptop using the web browser and say upload file and just push it to H2O. And that's fine for small data. But for big data, it's really not so practical.
So what do you do in that case? You just communicate with the database directly, or do you?
Well, we have
Or do you want to run a script that runs through R and says, "Oh, database, go through here." And
let me pull up our studio again. And the piece of code that did that is this, right? And so here, what this did is my R session over here was sending over a socket a command to my cluster saying, import data from this path on the cluster side, actually. But that could have just as easily said HDFS:// something. And the cluster would have read from
you're actually using the
HDFS.
command to bypass R.
Yeah, so the R is giving H2O the command, and H2O is doing it. But the data never goes through R, and that's really important to understand. You could just as easily said, if it existed, it doesn't exist today, but what you could imagine is saying H2O.select, say, and passing a select command to H2O, which would then go and make a query to a database and probably do it fully parallelized, splitting up that select into limits and offsets, tons and tons of limits and offsets, mini queries that then get ingested in parallel from your clustered database, right? We haven't done that yet, but that's the kind of thing that's on the roadmap.
Actually, one of the things I noticed, I did a little bit of research for it maybe a few days ago. I noticed that you have one H2O dply function.
We do, yeah.
And I'm just thinking to myself, that's kind of interesting because dplyr has been out for about 6 to 8 months, and it's light years faster than dply.
Mm-hmm.
But the other advantage of dplyr is that it allows you to make database connections.
Okay.
You can call it, it actually allows you to, what you can do is you can do something in R. It will create the SQL code that connects to the database, and you can do it, and that brings it into R. But I would think you guys should be able to take that, something like that, and make some serious hay out of that.
Well, so what we've done is a bit different, of course. So what we've done is actually do an implementation of ddply, but we interpret the ddply in the cluster. So the way that we do it is we actually we figure out what the ddply was asked to do by the user, and effectively reverse engineer it and turn it into a syntax tree kind of a thing, and then evaluate the syntax tree inside H2O. So it's not at all like what you might expect it to be. It's distributing that syntax tree across the cloud, across the cluster. So it's sort of an interesting thing. I confess to not knowing that much about dplyr, but my understanding is that it's trying to push a lot of the work down into the database layer, which we don't do. Like for us.
Well, that's the thing. What I'm thinking about is that you're using it as a conduit, right? Basically, you're using the R command as a conduit between the database and the cluster.
Yeah, yeah.
Right. Which I think is a really good idea. I like that idea. That's always been, that's always a big problem with R, because it's in memory software.
Yeah.
Yeah.
So what you'd like to be able to do is pass messages between R and something, something that has a disconnection or a cloud connection.
Yeah, exactly.
And
Yeah.
handle it that way.
Yeah, exactly. So, with us, it's R telling H2O to perform a task, and then H2O doing it, and then sending a result back to R, which is a tiny little result. Read in this, terabyte file, okay, do it, and now hand back, 1 kilobyte of information saying, I did it, and here's the pointer to the thing in the cluster. But you never actually transfer the data through R. R is the glue language that the user is using to create, structure in their thinking.
So you have a help file that says, here's how to interpret that pointer.
Sorry?
If it's graphical, you have to have some kind of a way to let people know what they're expecting.
Well, what you're getting back is this, right? It's a data frame. It looks like a data frame to you.
Oh, I see.
And that's the thing, right? This is an H2O data frame. And you can do end row on it, and end call, and head, right? And they work. And you can, if you wanted to fish a column out of that and maybe, add 25 to the column and create a new column, you could. And it looks like R, and it feels like R because it is R. But underneath the hood, what's happening is we've actually got operator overloading happening here, where we can see, okay, if there's a plus sign, or if you're trying to do the add operator, and I've got an H2O frame and an H2O frame, then I'm going to take that, package it up into a little message, send it to the cluster, and then get a little answer back, right? So it's all using this magic of R expression interpretation and operator overloading to make it look like R and actually be R, but have the work be offloaded to the H2O cluster.
And it comes back looking like.
And it comes back looking like R, right? But the data never flows through R, which is why now you can scale, right? So that's the sort of the magic behind the scalability of R with H2O, is by using R for what it's good at, which is letting you express yourself, but not using it for what it isn't so good at, which is having gigantic amounts of data in memory, right? That's where R kind of struggles and falls down. And so that in itself is sort of the core problem that the company was created to solve, in fact. So when Sri started off thinking about how to attack this problem, the first approach that he took was trying to figure out how to make R faster, how to build a better R, how to scale R itself. And it's not easy to do that. It's very difficult to do that. R as a language has a lot of, it's so flexible that it makes that sort of problem very difficult to
It's also an interpreted language.
It's also interpreted, but also most of the things that people want to make fast aren't even written in R. They're already written in Fortran or C.
Or C++.
Or C++. And so then all of those challenges make having rewriting R to be faster very, very difficult. And so that was actually the original path that was taken for the company of H2O, but we have now kind of gone a different direction. Yeah?
Well, that's sort of my question. What's your business model?
I was gonna say,
How are you making
How do
it
you
go?
make money?
Sure. So the business model is the standard open source model of support for the product. I mean, we've got an open source product. You're free to download it. You're free to, it's Apache license, which is a very, not a restrictive license. You can do anything you want with the software. But it turns out that people that are, have businesses that they're running and building on top of machine learning, they want support. And so that's, we sell support. We also sell some enterprise features that are tailored towards companies as opposed to open source users.
but like the web interface and everything that you showed here is completely
Everything I
free
showed
to,
you
like
is
self-install on
is
your own
open
servers.
source. Yeah.
Cool.
Everything I showed you is open source. Everything here is built from our H2O GitHub repository, and everything in that GitHub repository is licensed with the Apache 2 license. Yeah. Question?
Who's using H2O right now?
Sorry, can you repeat
Who's
that?
using H2O right now?
Oh, let me pull up our website. We've got a number of customers on our sort of scroll wheel here. I guess it's not so easy to read them, but there's Cisco, eBay, Nielsen, PayPal, Bigwell, Rushcard. In November, we actually had a conference called H2O World, and we had, on the second day of that conference, we had a number of customers come up and actually talk about what they're doing with H2O, which is really pretty neat. So what I would, if you're interested in hearing more about that, I would say go, let me see if I can find it for you, H2O World. YouTube. But basically here you can see yeah, here there are a bunch of talks by customers. So Vinod, he worked for Rushcard. They were doing fraud detection. Nakam is working at PayPal. He's also a colleague of Chris Severs, who is at eBay, as well as Venkatesh, who's doing fraud detection at PayPal. There's I don't see it off the top of my head, but Hassan is doing, he's at a company called Share This, and they're doing ad stuff. Lucar Valera is from Cisco. He talked about a predictive model factory doing, trying to predict whether a particular customer would buy a particular product within a particular time frame, a propensity to buy model. So a number of different use cases that were spoken about at H2O World by our customers, which is great. We were super excited to get them to do that. Yeah, question?
Yeah, one of the slides I saw, you have one interface that you can use H2O on is Tableau. As kind of like some data visualization, how is it done without loading the world in, and how would you handle like updating the source data?
The answer is revealed by another YouTube demo. And let me just kind of fast forward this to a part that looks sort of interesting. What you have here is, this is a Tableau workbook, and of course the Tableau visualization things, and then over on the left, it's kind of hard to read. Let's see if I can make it bigger. You can see, that's a little better. Here you can see, these things say run k-means, run GBM, run GLM. It's pretty hard to read, but what's inside, that's a little better. What's actually inside these buttons, you'll be pleased to know, as part of the R user group here, is R. So Tableau actually has an R integration that they've been working on with rserve. I don't know if you've heard of rserve, but basically, if you run an R session with rserve, you can write R code inside little Tableau snippets that get sent off to the R session. And then the R session, if you've got an H2O R package installed, can send that work to a big data cluster. So, just as with R and H2O, with Tableau on R and H2O, the data never really goes through Tableau. You're using H2O to build the model and do some sort of reduction of, billions of rows to a small amount of things that you can show in Tableau. And so it's kind of.
Does that encapsulate the whole warehouse scenario?
Sorry?
Like doing data warehousing in Tableau using H2O, or is that kind of different?
Sorry, I'm not sure I can answer that question.
And
Yeah.
as an extension on that, so how does it replicate between, like, say, a Tableau client to a Tableau server? Like when I have to replicate environments like when I develop my book, I'll be developing in client, but if I were to publish it to a server,
Well, let me address it this way. What I would say is, all those things are socket connections, so you can provide IPs and ports and host the individual pieces wherever you want, right? But yeah, if you're gonna set up something and use R as an intermediary with RServe, you have to stand it up. If it's not running, it's not gonna work.
So
Time?
the towns you think of, Boston gets a lot of delays.
Sorry?
Boston gets a lot of delays. I mean,
Yeah, so is LaGuardia, that's your point.
So Daniel's kind of suggesting that we should wrap up here, so.
Yeah, we should wrap up. Yeah, I think we're out of time.
Okay.
We usually close
That was great.
at 9.